Hi everyone, this is Miss Ward. Tonight your notes are going to be on the motion in two dimensions unit, concept 3, and we'll be discussing free fall. So it's going to be a little bit of a step back from our vectors that we've been talking about, and kind of a step to where we were last unit, talking about acceleration and our different equations. But this case, we're going to talk about the specific example of a free falling object. So first of all, it's important to note that we're talking about constant acceleration in anytime we talk about free fall. Galileo Galilei dropped an object from the Leaning Tower of Pisa to study the idea of free fall. He concluded that if if the effects of air resistance can be neglected, then all objects in free fall have the same constant acceleration. So, with the exception of objects that have a very different effect of air resistance, such as a flat piece of paper and a crumpled piece of paper. If air resistance is similar on either object, it does not matter how much that object weighs. They will fall at the same rate no matter what. And this applies to everything, so regardless of their size or weight. However, the only exception is that the air resistance must be small enough that we can ignore it. If air resistance comes into play, then things do not fall at the same rate because the air trapped underneath it will slow the object down. This theory was proved when they carried out an experiment on the moon, where they actually dropped a feather and a hammer at the same time. There is video of them dropping the feather and the hammer on the moon, and they fall at the exact same rate. We can also do this in a vacuum on Earth to prove this theory, but the only example we have of a non-man-made environment in which we're able to test this is on the moon. And the reason this works on the moon is because there is almost no atmosphere on the moon, so there's no air resistance, so it doesn't matter if the object would normally have air resistance on Earth. Like a feather would normally have a lot of air resistance. Well, on the moon there is no air resistance, so it falls at the same rate. So it's important to make the distinction when we talk about free fall that we're not always meaning that the object is moving downward. If you toss something in the air, it's in free fall on the way up and on the way down. And its acceleration is constant the entire time until it hits the ground, and the acceleration is due to gravity. Free fall only means that the only force acting on the object is gravity. Any object where the only force is acting upon it is gravity is in free fall, which means anything that's in the air, regardless if it's on the way up or on the way down or on the way to the right or the left, doesn't matter. If the only force acting on it is gravity, then it is in free fall. So the acceleration produced by gravity at Earth's surface we denote with a g, like the letter G, or a with the small letter g. So it's the acceleration due to gravity. For all of our calculations, g will equal 9.81 meters per second squared. That is a number that, while I don't tell people they have to strictly memorize it, you will memorize it by the end of this unit even, because we will use it so often, and you may already have it memorized because we've already used it several times. The direction of the motion determines if it's 9.81 meters per second squared or negative 9.81 meters per second squared. When trying to determine if you use a negative or a positive, I always tell people to try and think about if gravity is working in the favor of the object or against the object. If we are discussing an object that is being tossed up into the air, if you're going up, then gravity is working in the opposite direction of your motion, so you would use a negative 9.81. If you're falling down, if you're like jumping off of a cliff, for example, then gravity is increasing your speed, it is increasing your motion, you're going the same direction, so you'd use a positive 9.81. So always think if gravity is working for you or against you. When we discuss free fall, we can look at it in terms of position and velocity. In terms of position, the position of an object changes more than the velocity each passing second, which means that distance is actually increasing with the time squared, which is referred to as a parabolic relationship. And this will come into play more when we start looking at our equations later. Velocity in free fall, when the velocity of an object in free fall increases by the same amount of each passing second, which means that velocity increases linearly with time, and this is referred to as a linear relationship. Okay, so let's do a quick example where we look at an example of free fall. A boy steps off the end of a 3-meter high diving board and drops to the water below. A, how much time does it take for him to reach the water? And B, what is the boy's speed on entering the water? Okay, with this problem, we're going to be using our equations we had last unit. So for the very first one, when we're trying to discuss the position, first let's write down our givens. For letter A, they want us to solve for time. Time is what we're solving for, so time we don't have. Our final position is going to be 3, and since our initial position is 0, we don't have to worry about the change in position for this equation, just the position. Acceleration is our acceleration due to gravity, which is 9.81. Since we're going the same direction as gravity, we'd keep that as a positive. And our initial velocity is 0. Alright, so if you look at our equations list, you should find that x equals initial velocity times time plus 1/2 acceleration times squared is the equation we're going to be using in this case. Our position, again, is 3.00 meters equals our initial velocity, which is 0, plus 1/2, 9.81 meters per second squared, times the time squared. So again, we're solving for time. So 3.0 meters equals 4.905 meters per second squared times time squared. Divide both sides by that. You should end up with 0.612 seconds squared equals time squared. Take our square root. And you should end up with a time of 0.782 seconds, and you should leave it in 3 significant figures because we had 3 significant figures to start off with. So that is our answer for letter A. For letter B, we are trying to solve for our final velocity. Now we have a time, so our time is 0.782 seconds. We have an x of 3.0. We have a acceleration of 9.81 meters per second squared, and an initial velocity of 0. Final velocity is what we're looking for. Now you could use a variety of equations since we have so many of the pieces. I'm going to use the VF equals VI plus AT and use our time that we just solved for. So final velocity is what we're solving for. Initial velocity is 0 plus 9.81 meters per second squared times our time of 0.782 seconds, and you should get final velocity equals 7.67 meters per second. And that is your answer. Keep in mind with these that you will definitely need to be keeping those equations handy that we used in our last unit. You will definitely be using those as we progress through this unit. Not just for free fall, but when we start getting into the 2 dimensions, they're definitely going to be important, so make sure you keep those on hand. Okay, fill out your WISC online. Remember, there will be a quiz tomorrow in class, and if you have any questions, please let me know. Thanks, have a great night.